So chapter number 7, oscillators and waveform generators. Again, the last chapter that deals with oscillators or well, Schmitt triggers and comparators that changes their state, goes to the V saturation and negative V saturation at certain values. Oscillators, they do the same thing, although oscillators, they keep switching between V saturation and negative V saturation. Well, there are 3 different types of oscillators. We're going to discuss the 3, but the one that we are going to concentrate on, they are the one that can generate a square waveform, basically, from your biasing voltage, from your DC voltage. So we are not giving any input sinusoidal signal or any input signal except our DC biasing. But from the DC biasing, basically, you can get an output which is an oscillating signal. That's the property of oscillators. So as you can see, the first bullet point, oscillator and waveform generators are circuits that produce an AC output from a DC source. That DC source, they are your biasing voltages. They will always have a positive feedback because when you have the positive feedback, then you are creating instability in the circuit that you can switch between the V set and negative V set. Most of the oscillators are going to they produce rectangular waveform or a square waveform based upon the duty cycle. You don't really get many oscillators that produce sinusoidal waveform. But if you want a sinusoidal waveform, who's going to tell me how we can get a sinusoidal waveform from an oscillator that is producing a square waveform? Say it again. Okay, so integrator is going to produce, if you integrate the square wave, it is going to produce a triangular waveform, not sinusoidal waveform. No, that's going to produce impulses. Anyone? You guys did that. You guys did that in one of the classes. Say it again. RF? What do you mean? RF what? Huh? Oh, in some of the classes you did that. Oh, exactly. Here's the answer. Square waveform means what? That it has fundamental component, it has harmonics, and it may or may not have an average component. So if you want your sinusoidal waveform, you can extract the fundamental component. If you want the same frequency, you can extract the fundamental component, and your square wave is going to give you a sinusoidal waveform. And you did that in which class? Circuit analysis, lab number 5. That's what you did. You created a filter to extract the fundamental component from a square wave. I know that because I wrote those labs. So if you do need sinusoidal waveform, again, you can always extract the fundamental component or any harmonic if you want different frequency to get the sinusoidal waveform, basically, from a square oscillatory waveform. 2 methods to produce oscillations. The first one is what we are going to use mostly, RC circuit to produce oscillations. So RC circuit, capacitor charge and discharge, is going to produce an output that will oscillate between V saturation and negative V saturation, and that's what we are going to use, the timing method. And then there is another method, unity loop gain method, in which we keep the gain at 1, and keeping the gain at 1 can also produce the steady state oscillation for certain oscillators. But in this chapter, all different circuits that we are going to study, we are going to use timing method for each circuit to produce an oscillator. There are 3 different types of oscillators. They are also called multivibrators because they vibrate at different levels. The first one is monostable. There is only one state is stable. It goes to that state, stays there for a period of time, and then goes back to the other state, which is the stable state. So it's only one state that is stable, the other is unstable. It just stays there for a period of time, then goes back to the stable state. And in digital systems, you guys have discussed one short circuits in digital systems, I'm assuming, or no? It was part of digital systems too. When I used to teach digital systems too, we used to discuss one short circuits, which is one of the oscillators, which are monostable oscillators. I don't know if, because I have not taught the new digital systems course, the combined one. So I'm pretty sure with the combined course, they must have taken out some stuff to combine both digital 1 and digital 2 into a single course. So I don't know if one short circuit is still part of that combined course or not. Anybody remember? Anybody? You don't remember? So maybe they took it out. Maybe they took it out. There was a lab on that as well, if I remember correctly. Anyways, so again, that's what I put in digital systems because I taught digital systems 1 and 2 both, and at that time we used to discuss that in digital systems 2, one short circuit. But those are monostable circuit. Bistable circuit, both states are stable. It goes to one state, it stays there as long as you want it to stay there, and then it can go back to the other state based on the input condition. And that's the example of flip-flops that they are bistable circuits. And then what we are going to study, they are astable circuits. That is, no state is stable. It keeps going from high state to low state with a certain time period and certain frequency and certain duty cycle. So those are the oscillators, astable circuits. Operational amplifier is stable multivibrator or oscillator. So they don't have any stable state, as we discussed. This is the basic circuit that you can see here. And as you can see, you have the capacitor and resistor circuit. They're connected in series, of course, because no current goes in either the inverting input or the non-inverting input. So that resistor, that capacitor, and the output, they make a circuit that is a series circuit. And at the non-inverting input, you have the output and the two resistors, R1 and R2, they make a series circuit. So what will be the voltage at V positive? Who's going to tell me? What will be the voltage expression at V positive? How are we going to find it? Voltage division, of course. Since V out, R1, R2, they are in series, or they act as in series. We can apply voltage division, and the V positive voltage is the voltage across R2. So that's simply V out R2 over R1 plus R2. And remember, V out, it goes between V saturation and negative V saturation. So the value of the voltage at the non-inverting input is going to switch between negative V saturation R2 over R1 plus R2 and positive V saturation R2 over R1 plus R2. We call this expression, let's say V1, because that's the variable I will be using to represent this V out R2 over R1 plus R2. Okay, so we'll start analysis when output has achieved a steady state. It's going to take some time for the capacitor to charge, discharge, and then come to a steady state. Then it is charging and discharging between the two levels. So we are going to do all the analysis when it has achieved that steady state, that it is charging and discharging between the two levels with a specific time period. Before that, of course, it's going to increase, charge and discharge until it will hit that level. So this is V1, R2 over R1 plus R2 ECET. If your output is at saturation, if it is at negative V saturation, then this is going to be negative V1, R2 over R1 plus R2. negative VSET. So assume that the transition to VSET happens at the reference time t is equal to 0. So at any reference time, we assume that the output goes from negative VSET to positive VSET. So this is t is equal to 0. VSET and negative VSET. Let's assume that the transition is happening at t is equal to 0. That's our reference time. The voltage at the non-inverting input of the op amp at t is equal to 0 positive can be calculated using the following equation. So the voltage at the positive terminal is going to be V1 is equal to R2 over R1 plus R2 VSET, because at t is equal to 0 positive, that is just after t is equal to 0, it has jumped to positive VSET. At the inverting input, you have the circuit, V output. So the current, basically this is your circuit. V output, R and C. They appear to be connected in series because again, no current is going to flow in the inverting terminal, into the inverting terminal. So they will appear to be in series with each other. And that's what you see over here. Remember, the output is switching between VSET and negative VSET. So this is your output waveform. And then this is your series RC circuit. So the voltage at the inverting input, remember inverting input is connected to the capacitor. So whatever the voltage across the capacitor, we see capacitor voltage is equal to the same voltage at the inverting terminal. So voltage at the inverting terminal is the capacitor voltage. And we know that when you have a series RC circuit or any RC circuit, the capacitor voltage, and this is your source, capacitor voltage, what you learned in circuit analysis, is comprised of two components. One component will be the steady state value of the capacitor voltage, and the other component is going to be the natural response or the transient response of the capacitor voltage. So that's what you studied in circuit analysis as the complete response of RC circuits. So you did complete response of RC circuit, RL circuit. So this is the complete response of RC circuit. That is the steady state value plus the natural response. The steady state value, how do you calculate it? You let the circuit run for a very long time, and then you see what is the voltage that is accumulated, that is going to accumulate across the capacitor. So if you run this circuit for a very long time, and the output is at VSET, and if you're running the circuit for a very long time, then the capacitor is going to become open circuit, and it is going to be at the same voltage as the output voltage, which is at VSET. So capacitor voltage, steady state voltage, and the output voltage is going to be the same after capacitor is fully charged. And that is what you see over here, that if the output is at VSET, the steady state value of the capacitor voltage is going to be VSET, and then the natural response is written, usually the exponential function a e to the power negative t over tau. Tau is the time constant of the circuit, which is RC. That's coming directly from your circuit analysis class. How do you find the value of A? Using the initial conditions. Again, going back to circuit analysis, you used to employ the initial condition to find the value of A. Initial condition, that is, what is the value of the capacitor voltage just before the change is going to happen. Now remember, what is the property of the capacitor as far as voltage change is concerned? Say it again. No sudden voltage change. Capacitor resists the voltage change. The voltage just before any change is happening is the same as just after the change is happening. And remember the switch, when you open the switch or close the switch, just before the switch is opened or closed, the voltage across the capacitor is going to be the same as just after that switch is opened or closed. So the voltage, remember the voltage is going from negative VSET to positive VSET. So at t is equal to 0 or t is equal to 0 negative. So remember this, just before t is equal to 0 is t negative is equal to 0 negative, and just after that is t is equal to 0 positive. So that's how we designate, just before the instant and just after the instant, 0 negative, 0 positive in this case. Just before the change happens, the output voltage was negative VSET. And if the output voltage was negative VSET just before the change happened, that means at the non-inverting terminal, the voltage was negative R2 VSET over R1 plus R2 or negative V1. So at this time, T0 negative, the voltage at the terminal, positive terminal, the value was negative V1. And since the non-inverting voltage is equal to the inverting voltage, the inverting terminal, that means just before the change happened, the capacitor voltage was negative V1. And since the capacitor resists the change of voltage just after the change, that is, once the output goes from negative VSET to positive VSET, the capacitor is not going to go instantaneously. It is still going to show that it has the voltage negative V1, and then it's going to start changing slowly. So that's your initial condition. So tau is the time constant. It can be seen that if the current run for a long time, we said blah, blah, blah. To calculate the value of A, evaluate at the initial condition at 0 positive, since the capacitor cannot change instantaneously. VC0 negative is equal to VC0 positive. Before the transition at t is equal to 0, output was negative VSET. Output was negative VSET, and V positive 0 negative was at negative V1. Since they are the same, therefore VC0 negative is negative V1 as well. So that's our initial condition. Initial condition. And we're going to use that initial condition to calculate the value of A. So that's what we are doing over here. V negative at 0 positive will be equal to VC0 positive, V saturation plus A, and the value of VC0 positive is the same as VC0 negative, which is VC0 negative, which is negative V1. So negative V1 is equal to VSET plus A, and A will be equal to negative V1 minus VSET. And remember, negative V1 is R2 over R1, R2 over R1 plus R2 times VSET. R2 over R1 plus R2 times VSET. So this is negative, negative. That's negative V1. So we're going to go ahead and plug this value of A right over here. And our equation for the capacitor voltage is going to be VSET minus V1 plus VSET e to the power negative t over tau. So the capacitor voltage, now this is your output voltage, which is switching between VSET and negative VSET. At t is equal to 0, it switched from negative VSET to positive VSET. This is the voltage at your V positive, the non-inverting input, which is switching between V1 and negative V1. And then this is the capacitor voltage that shows you the pattern of charging and discharging of the capacitor. So at t is equal to 0, the value of the capacitor voltage was negative V1, as we discussed right over here. V negative at 0 positive was negative V1. So it is at negative V1. And then it starts charging. The capacitor starts charging because the output goes from negative VSET to positive VSET, and the positive input, it goes from negative V1 to positive V1. So it starts charging, and if there is no hindrance, it's just going to charge all the way to VSET, as we discussed right over here. If we let it go, then it's just going to charge up to VSET. However, as soon as it is going to hit the value V1 and exceeds that value just a little bit, what is going to happen is the value at the non-inverting at the inverting terminal is going to become more than the non-inverting terminal, because right now the value here is VSET, and then this is charging. This is charging from negative VSET, negative V1. So this is at V1. It's going from negative V1 to VSET. But as soon as it's going to hit V1 and exceeds a little bit, then the voltage here is going to become more than the voltage over here. That means that the differential voltage is going to become negative between V positive and V negative, and the output is going to go from VSET to negative VSET right away. And that's what happens over here. As soon as it will hit V1 and exceeds a little bit, and we are calling this time as T1, then the output voltage is going to switch from VSET to negative VSET. V positive is going to switch from V1 to negative V1. And then the capacitor start discharging from V1 into the opposite direction, that is negative V1. And again, when it will become a little bit smaller than negative V1, your differential voltage become positive again, and the output is going to jump to VSET, and V positive is going to jump to V1. And this cycle is going to keep on going. And that's how this circuit is going to operate based on the timing of the capacitor and resistor circuit, RC circuit. It will keep oscillating between VSET and negative VSET. And capacitor will keep on switching or charging and discharging between V1 and negative V1. Any question about how the circuit is operating? And once again, guys, it's very important for you guys to go sit down and then read it and try to understand it. Because at this time, of course, you get like, let's say 10-15% of what we are studying, understandable. But once you have time, you have the annotated notes, you're taking your own notes, then make sure that you study it again. Don't just jump to the exercises, study the topic to understand the topic properly before you do the exercises. So that's very important. Okay, at this time, we're going to take a break and then continue from here after the break. Okay, so the capacitor voltage, of course, is charging and discharging. Output voltage is going between saturation and V saturation and negative V saturation. As you can see that the total time period of the output, half of the time the capacitor is going to be charging and half of the time it's going to be discharging to the value of V1 and negative V1. So the time T1 is basically half of the time period, which is T by 2. So how do we find the time period of the output? We use the capacitor equation, and at time t is equal to T1, which is half of the time period, we know that the capacitor voltage is going to be charged to the voltage V1. And that's what we did over here in the capacitor voltage equation, because this is the capacitor voltage VCT. We evaluated the capacitor voltage at time T1, which is half of the time period. And at that time, the capacitor voltage is V1. So we put down that V1, which is equal to VSET minus V1 plus VSET, e to the power negative T1 over tau. And then we simplified this. And T1 after simplification is tau natural log of VSET plus V1 over VSET minus V1. And the time period, since T1 is T by 2, so the time period is 2 times T1. So the time period of the output waveform is 2 tau natural log of VSET plus V1 over VSET minus V1. And we went ahead and replaced the value of V1 and tau, or V1, not tau, sorry. Replace the value of V1. Tau, of course, is RC. So tau is RC, and we replaced the value of V1 here and V1 over here. And then we simplified it. And this will be our equation for the time period after simplification. 2 times RC natural log of 1 plus 2 R2 over R1. So the time period is directly proportional to the time constant RC, as you can see. The longer the value of time constant, the longer the time period of the output is going to be. When we are designing the circuit, we can create, we can take one of the considerations into account. That is, we can choose R2 to be equal to 0.86 R1. And that is going to give us 1 plus 2 times 0.86. And natural log of 1 plus 1 plus 2 times 0.86, the natural log of this that whole quantity is going to be 1, which will give us basically the time period to be equal to 2 times the time constant, which is 2 RC. So that's one of the design considerations that we can take. Again, this is not a must situation, but this is one of the things that you can do to simplify the time period, the equation of the time period. Another consideration that we have to take, of course, is that we have to use the capacitor to be electrolytic capacitor, because the voltage across the capacitor is changing, positive and negative. It's changing its polarity. So you cannot use the ceramic capacitor, because ceramic capacitor is unipolar, basically. It's opposite. Okay, electrolytic is unipolar. There, you're right. So you have to use the one that the polarity can change. So I'm going to go ahead and change. Voltage across change polarity, electrolytic must not be used. Oh, so yeah, that's the statement is correct. Electrolytic capacitor must not be used. Ceramic must be used. That is true. One of the examples, it's already solved, but let's go over it. Again, even the example is solved, make sure that you solve it again without looking at the solution, and that gives you very good practice. And if you make a mistake, then you can go and check that mistake as well. So circuit is given to you, which is your astable oscillator. And this is the capacitor value, this is your resistor R, this is your R2, and this is your R1. These are the variables. Threshold volt, but we're not calling it threshold voltage, just the voltage at which it is going to switch. You can call it threshold voltage, but it's a feedback voltage, V1, which is going to be the voltage right over here at V positive. R2 VSET over R1 plus R2, which will give you 5.2 volts. So that's going to tell you at what voltage the capacitor is going to switch from charging to discharging. So at 5.2 volt, when it is going from negative 5.2 to positive 5.2, as soon as it will hit positive 5.2 and exceeds a little bit, it's going to start discharging towards negative V saturation, but it's not going to hit negative V saturation. It's going to hit negative V1, and then it's going to start charging again. And the output will switch from V saturation to negative V saturation, and then negative V saturation to positive V saturation. Time period of the output waveform Again, it's simply putting the values and calculating the time period in the equation. And the time period comes out to be 0.4067 millisecond. And from the time period, we can calculate the frequency, which is the reciprocal of the time period. The frequency of the output will be 2.459 kilohertz. So simply all the equations, and then you're calculating the values from those equations. 7.2 again, I solved it already. Design an astable multivibrator with output frequencies to be 10 kilohertz. Also calculate the feedback voltage if V saturation is positive, negative 13 volt. So one of the design consideration, as I said, we're gonna go ahead and consider that. We're gonna take R2 to be equal to 0.86 times R1. So we're gonna put over here 0.86 times R1. R1 will be cancelled out, and natural log of 1 plus 2 times 0.86 is going to be 1, which will give us the time period to be equal to 2 times RC. R1 is 10 kilo ohm, R2 can be 8.6 kilo ohm in order to have this relationship. And then we want the frequency to be 10 kilohertz. That means the time period in this case is going to be 1 over 10, 0.1 millisecond. So as I have told you multiple times that since capacitor values are limited, resistor values, we can have many values, plus we can make combination of resistor. It's better to take a capacitor value when you are designing a circuit. In this case, of course, we don't know R, we don't know C. We're gonna go ahead and choose one of the values in order to get the time period of 0.1 millisecond. So we choose capacitor value to be 10 nanofarad. And from that, we calculated the resistor value to be 5 kilo ohm, which is fine, which is perfectly fine resistor value. Again, if 5 kilo ohm is not available, a standard resistor, then we can always make combinations to get to 5 kilo ohm. I'm pretty sure it's available though, 5 kilo ohm. 5.1 is available, I know. 5.1 is standard value. And from that, we can calculate the feedback voltage at which your capacitor is going to switch direction. And that voltage is 6.0108 volt. All right, guys. 555 timer is one of the most commonly used ICs in, for oscillators. And it's an 8-pin IC. You're going to use it in the lab, I think lab number 6. I think next week we are doing lab 5 and lab 6 both, right? Make sure you do the pre-lab. And remember, pre-lab includes what? Pre-lab includes all the theoretical derivations, understanding of what you're doing. All the circuits must be simulated. Results must be collected. So 555 timer is the IC that you're going to be using to create an oscillator. And it's an 8-pin IC. And you can have all 3 types of oscillators that you can create with 555 timer. You can have monostable oscillator, bistable oscillator, and astable oscillator. A lot of application of 555 timer. Again, it's a very simple circuit that you can create to produce oscillations. So it can be used anywhere where different oscillations are required. One short circuit, delay timers, pulse generators, lamp flashers, alarm, tone generators. A lot of applications that you can use that the 555 timer can be used. All right, why did it get the name of 555 timer? Because it has internally collected 3 5 kilo ohm resistor, which it uses to generate the 2 comparator reference voltages. That is your VSET and negative VSET, or 2 reference voltages. So you have this 5K, this 5K, and this 5K. And that's why the name 555 timer. And these 35Ks basically they act as voltage divider to produce the voltages at the negative input of comparator number 2 and the positive input of comparator number 1. And this is the internal circuitry, as you can see. So let's go back to the circuitry. So 8-pin IC, as you can see, you have pin 1, 2, 3, 4 on the left side, and then 5, 6, 7, 8 as the usual readout of the pins. Pin number 1 is grounded to trigger. So pin number 1 is grounded. Pin number 2 is trigger, which is connected to the inverting input of comparator number 1. There are 2 comparators, as you can see. Pin number 3 is the output. Pin number 4 is the reset pin. 5 number is control voltage. Control voltage is connected to the inverting input of comparator 2. And pin number 6 is the threshold, which is pin number 6, which is the connected to the non-inverting input of comparator 2. And pin number 7 is discharge, and 8 is your VCC. So it's a single power supply, single biased voltage power supply, and then you have the ground. You don't really need the VCC and negative VCC for 555 timer. If pin number 5 control is not connected to any external DC voltage, then the voltage at the inverting input of comparator 2 will be 2/3 of VCC, and voltage at the non-inverting input of comparator number 1 will be 1/3 of VCC. So pin number 5, let's go back to the circuit. Pin number 5 is the control. If we leave it open, it's not connected to any external DC voltage, then you're going to have the voltage at the inverting input to be the voltage across these two 5 kilo ohm resistors. So the voltage here is going to be 2/3 of VCC because you have 3 5 kilo ohm resistors. And remember, they will appear to be in series with each other because the current is not going to flow in the operational amplifier. So this is going to be 2/3 of VCC over here if control is left open, and you're going to have 1/3 of VCC at the inverting non-inverting input of comparator 1. That's what it is said over here. If pin number 5 is not connected, voltage at the inverting input of comparator 2 will be 2/3 of VCC, and at the non-inverting input will be 1/3 of VCC. And these two voltages are going to produce basically the threshold for the transition levels. So since this will be 2/3 of VCC, if comparator number 2 voltage voltage at the threshold, if it exceeds 2/3 of VCC, then the output of comparator 2 is going to be high. And if it is less than 2/3 of VCC, then the output of comparator 2 will be low. And likewise, comparator 1, if the input at negative terminal, at the trigger basically is less than 1/3 of VCC, then the output of comparator 1 will be high. If it is more than 1/3 of VCC, then the output of comparator 1 will be low. Again, remember, comparator is just going to produce the output based upon the differential voltage, if it is positive or negative. This is the table that shows different pins and their function and where they're connected basically. Pin number 2 is trigger pin. It works like a starter pistol to start 555 timer running. The trigger is an active low trigger, which means that the timer starts when voltage at pin 2 drops below 1/3 of supply voltage, as we discussed. When the 555 is triggered via pin 2, the output on pin 3 goes high, which is the output. How does it operate is given in this table. There are 4 conditions. Trigger, which is pin number 2, which is connected to the inverting input of comparator 1. So this is inverting input, so V negative of comparator 1. Threshold is connected to the positive or the non-inverting input of comparator 2. Output is pin 3 that will go between V saturation and negative V saturation. And discharge state is pin number 7, which is discharge. And it has different function if it is open, left open, if it is grounded, and so on and so forth. All right, so condition number A is when your trigger, which is the non-inverting, which is the inverting input of 1, is below VCC by 3. And pin number 6 is going to be below 2 VCC by 3. So pin number threshold, which is pin number 6, keep forgetting, pin number 6, and pin number 2. Pin number 2. If threshold is below, if trigger is below VCC by 3, and your threshold is below 2 VCC by 3, the output state is going to be high, because you're going to have this comparator giving high, this comparator giving high flip-flop, whatever the internal circuitry, and output is going to be a high state for this combination. Condition B is if V inverse is below VCC by 3, but threshold is above VCC by 3. Then it's just going to remember the last state. Whatever the last state was, either high or low, that is going to be the output. And likewise, condition C and condition D that are given to you. Condition D is if both are above VCC by 3, then the output is going to be low. Discharge pin is important because it can be either open or grounded. And it's going to remember the last state. That means either it's going to be open or grounded, because we're going to use that discharge state in order to create a timing circuit. So this is how the 5-5 timer is going to work based upon the voltage at this pin and the voltage at this pin, pin number 6 and pin number 2. And once again, the voltage here is 1/3 of VCC, and the voltage here is 2/3 of VCC. And that's what you see here, 2/3 of VCC and 1/3 of VCC. Basically, it is compared, pin number 6 and pin number 2. Pin number 6 and pin number 2, they're compared against 2/3 of VCC and 1/3 of VCC in order to change the states. All right, this is a circuit that is generally you create to set the timing of the output. Again, it's a circuit that uses or that employs capacitor, and charging and discharging of capacitor is going to set the output time. For normal operation, pin number 4 is connected to VCC. Pin number 4, which is right here, is connected to VCC. Since it is an active low input, it activates when the input is low and resets the output of the timer. Pin number 5, which is right over here, is bypassed to the ground through 0.01 microfarad capacitor for normal operation. This will set voltage values of 2/3 of VCC and 1/3 of VC at the inverting input of comparator 2 and the non-inverting input of comparator 1. Pin number 2 is trigger right here, which is pin number 2 and pin number 6. They are shorted out, as you can see in this circuit. So remember, all the operation is happening when the conditions are changing in pin number 2 and pin number 6. So those two we are going to tie up in the circuit and then connect them to a capacitor which is grounded on the other side. So the voltage at pin number 2 and pin number 6 will be the same, which is the voltage across the capacitor. And then you have two resistors RA and RB that you see that will be used to set the timing. So timing of the circuit is going to be set by RA, RB and capacitor. Output will move between high level, high voltage and low level, which is 0 because it's a the biasing is done only positive and 0. So it's gonna go from the positive value and ground. Voltage across the capacitor is the same as pin number 2 and 6. It will oscillate exponentially between 2/3 of VCC and 1/3 of VCC because the condition on those two pins, as we discussed, is going to change when the voltage here is going to exceeds or reduced below 2/3 of VCC, and the same thing is comparator number 1. The condition is going to change at 1/3 of VCC. It's going to go high or low below that. All right, how the circuit is operating. Again, we're going to get to the steady state value. So this is your output, high voltage and low voltage. The high voltage time is T high, so this is T high, and the low voltage time is T low. And observe that they are, it says rectangular waveform, it's not a perfect square waveform. That shows you T low is smaller than T high. So the duty cycle is more than 50% in this case. This is the capacitor voltage that is charging from 1/3 of VCC to 2/3 of VCC in the time T high, and then it is going from 2/3 of VCC to 1/3 of VCC in the time T low. And as the capacitor voltage charges and discharges, pin number 6 and pin number 2 values are going to change, same value between 1/3 of VCC and 2/3 of VCC. We take any reference time t is equal to 0. We assume output goes from 0 to the highest state, and the discharge pin number 7 goes to the open state. So if we go to pin number 7, which is right here, pin number 7 is discharge pin. The pin is used to discharge an external capacitor that works in conjunction with the resistor to control the timing. In most circuit, pin 7 is connected to the power supply through a resistor and to ground through a capacitor. So pin number 7, when the output goes to high state, pin number 7 goes to an open state. So open circuit. At this time, VC0 positive, which is equal to VC0 negative, is going to be VCC by 3. So right here, at the start of our reference time, output goes from 0 to high voltage, and the capacitor voltage, since it cannot change instantaneously, the value VC0 positive and VC0 negative is going to be at VCC by 3. Since discharge is in open state, VCC, the two resistors and the capacitor will make a series circuit. So discharge pin 7 is open. So you have VCC, RA, RB, and the capacitor. They are going to make a series circuit. And this is the series circuit that you can see. VCC, RA, RB, and the capacitor. Across the capacitor, you have the voltage. VCC by 3 at the start of the cycle. It's a first order transient circuit. And again, we can write the equation for the capacitor voltage, which is the steady state value plus the natural response. The steady state value from this circuit is when we let the circuit go for a very long time. When the capacitor is going to be fully charged, the value across the capacitor is going to be VCC. And that's what you see right over here, which is a steady state value of the capacitor. When we let it run for a very long time, it's going to go to VCC. And of course, your the value of your transient response, the expression is A e to the power negative t over tau h. So since we have two different circuits, as you will see, for the first circuit, when you have RA, RB, and C, tau h represents the series combination of RA plus RB times C. To find A, we use the initial condition at t is equal to 0 positive when the capacitor voltage was VCC by 3. So this capacitor voltage is VCC by 3 at the initial condition. And when you put it here, VCC by 3 is equal to VCC plus A e to the power negative t over tau h. Then you are going to get that A value is negative 2 VCC over 3. When you plug that in equation 7.9. So capacitor will start charging towards VCC as per our equation. This equation is going to start charging towards the steady state. As soon as it will cross 2 VCC by 3, both pins 2 and 6 will be above VCC by 3 and 2 VCC by 3 respectively. And according to the condition D in the table, as we discussed, condition D in the table, pin number 2 will be above VCC by 3 and pin number 6 will be above 2 VCC by 3. The output is going to go down to 0 and discharge pin is going to go to the ground level. So it's going to start charging. Remember, it's charging towards VCC, but before it will hit VCC, it's going to hit 2 VCC by 3. As soon as it will hit 2 VCC by 3, then this condition is going to be true because both pin number 2 and pin number 6, they are tied together. So VCC is above 2 VCC by 3, pin number 6 is above 2 VCC by 3, and likewise pin number 2 is above VCC by 3. If it is above 2 VCC by 3, of course it is above VCC by 3. The output from the highest state is going to go to the lowest state, and pin number 7 is going to be grounded. So pin number 7 will be grounded, and the output is going to go from high to low. When pin number 7 is grounded, now you don't really have any voltage connected to RA, RB, RC. It's going to be voltage, pin number 8, voltage connected to RA and then going into the ground. And then you have this circuit with ground, RB, and capacitor. And that's what you see over here. Pin number 7 is grounded. RB and C will make a source-free natural circuit as shown here. RB, C, and then of course you will have a ground. Capacitor is going to start discharging. It already has the voltage 2 VCC by 3 accumulated. So this voltage is going to run a current through the resistor RB and it will start discharging through RB. When it is discharging, it will hit VCC by 3. And as it will hit VCC by 3 and it starts going down, this condition is going to be satisfied, condition number A, that it is pin number 2 is below VCC by 3 and likewise pin number 6 is below 2 VCC by 3. Because if it is below VCC by 3, then definitely it is below 2 VCC by 3 as well. And as soon as this condition is going to be satisfied, output is going to go back to the highest state, discharge state will be open, and then condition D is going to be satisfied when it will start charging again. So this circuit. Capacitor voltage can be represented by 2 VCC by 3, A e to the power negative t over tau L. This is the initial value of the capacitor voltage. when it was charged to 2 VCC by 3, and then it's going to start discharging because it's only the natural circuit. It's not a forced circuit. So it's going to start discharging. It's going to take some time to discharge. And the time constant of the circuit now is tau L, which is RB times capacitor. So this charging and discharging will keep on happening of the capacitor, and the output will keep switching between high value and 0. What is the time period? Remember, the time period in this case is the high time plus the low time. This is the total time period. So first we will figure out what is the high time, and then we'll figure out what is the low time. And the combination of both is going to give us the total time period. High time we can figure out from our first circuit, from 7.10 equation, which is the equation for the first circuit. So when your time is TH, the value of the capacitor is 2 VCC by 3. And that's what we use here. At time TH, value of the capacitor voltage is 2 VCC by 3. We plugged that in, solved it, and found that the time TH is tau H, natural log of 2, which is equal to 0.693 RA plus RB times C, because tau H is RA plus RB times C, and natural log of 2 is 0.693. To find the low time, we go to the equation 7.11 that corresponds to the low time, and again we go all the way up to low time, where your value is going to be 0.693 RB times C, which is this equation, this equation. Because the value of the capacitor voltage at the low time is going to be 1/3 of VCC. So we put 1/3 of VCC over here, and then find the value of the time TL, and it's going to come out to be natural log of 2 times tau L, so 0.693 times RB times C. And we combine the both to calculate the total time period. And the total time period comes out to be 0.693 RA plus 2 RB times C. The high time and low time are different, because the capacitor discharging and charging circuits are different. They're not the same circuit. Tau L and tau H both are different. Therefore, TL and TH are different as well. We can calculate the duty cycle. It's going to be always greater than 50%, because your T high has longer time than TL. So duty cycle is high time over the time period, TH over T times 100%. So this is going to be duty cycle. So it will always produce rectangular waveform. It's not going to produce a square waveform, but at least theoretically, if we do want to produce a square waveform, at least theoretically, this is the arrangement that can be done. We create a diode between pin 7 and pin 2. Now, how it is going to work? Of course, when pin 7 is open circuit, the diode is also going to be open, because your forward biasing is going to be 0, and then of course it's connected over here, which has a higher voltage. The diode is going to be open circuit, and your circuit is simply going to be VCC, RA, RB, and C. And when you have, let me see, when output is high, pin 7 is open. No, when pin 7 is open, let me see. Oh yeah, when pin 7 is open, it's not going to be open circuit. It's going to be short circuit, because your voltage here is going to be higher than the voltage over here. Your voltage here, of course, is going to be VCC minus the voltage that is dropped here. And the voltage here is going to be VCC minus the voltage drop here and voltage drop here, whatever the capacitor voltage is, which is going to be smaller. So diode is going to act as a forward bias diode when pin 7 is open. And when it is forward bias diode, theoretically assuming that the diode, when it is forward bias, its voltage drop is 0, although it's 0.7 or 0.3 based on the diode type. But if we assume that the voltage drop across diode is 0 approximately, then it's going to short out RB, and your circuit is simply going to be RA, diode, and capacitor. So your time constant is going to be RA times capacitor in that case, which is right here. And when the output goes into the low state, pin number 7 is going to be grounded. When pin number 7 is going to be grounded, diode is going to go in the reverse bias configuration. And your natural circuit is going to be the same, RB times C. So the time constant is going to be RB times C. So if we keep RA and RB both the same value, then at least theoretically, we can have the high time will be equal to the low time, because the time constants are going to be the same. But again, practically diodes do not offer 0 on resistor, and also there is always some drop in the on state. So practically this method is going to make the duty cycle close to 50%, but not exactly 50%. But there's another way to have the duty cycle 50%, and that's if we add a counter at the output of 555 timer. Again, you guys discussed counters at least in digital systems, right? Digital counters, okay. And 7493 is one of the ICs that was discussed in digital systems, which is a 4-bit counter. So if you do want to have the output oscillating with 50% duty cycle, then you can create a circuit. Let's see. Let me see, what is this? All right. You can create a circuit something like this. So the output of 555 timer, which is the output 3, is the clock of the counter. And you have QA, QB, QC, and QD, 4 outputs. The time period of QA, which is TA, is double the time period of clock, if I remember correctly, 2 times the output, T out. If the time period here is T out, then it's double the time period of the output. Let me confirm. And remember, this T out is 2 times TL plus TH. The output of B is 2 times time period of TA, which is 4 times time period of T output. Time period of C is 2 times time period of B, which is 8 times time period of the output of your 555 timer, and time period of D is 2 times time period of C, which is 16 times time period of the output. And the output is just connected to the clock of 74 LS93 counter. Now, how does the counter work? Just to refresh your memory, that's the clock. Remember, the counter works at when the clock is going up. You have 4 flip-flops and in the counter. When clock is going up on the positive edge, then your output changes. So for clock at the positive edge, the output for QA or Q0. This is QA, this is QB, QC, QD. Yeah, I took the figure where it was Q0, but this is QA, QB, QC, and Q. So at the positive edge of the clock, QA is going to rise, and at the positive edge, again, is going to drop. So the transition only happens at the positive edges. And likewise, QB, since the clock of QB is the output of QA, which is this, at the positive edge of this is going to do the transition. And likewise, at the negative edge or positive edge, and one of them, negative edge, yeah, is going to do the transition. And the same goes for the other one. So whatever the clock is coming, irrespective of the duty cycle. Remember, duty cycle doesn't matter because you can have more duty cycle in high and low duty cycle, and I mean, you have more time in high and less time in low. Remember that the transition is what matters. So when the clock is connected, when this clock is connected to the output, irrespective of what is the high and low time, what it matters is when you're going to have the positive edge or negative edge, which is happening after one time period. So irrespective what is the high time, what is the low time, doesn't really matter. It's only the edge that counts. And that edge is going to just drive the output high and low for QA, and then QA is going to drive QB, and then QB is going to drive QC, and so on and so forth. So although here the clock is perfect square, but this is just a figure basically. If the clock is not perfect square, that's perfectly fine because only you need the edge. Time period is going to be the same. If you have 1 kilohertz, then irrespective of what is the duty cycle of that signal, as long as it is 1 kilohertz, 1 millisecond time period, at the start of each 1 millisecond, it is going to hit QA and the transition is going to happen. So by this combination, you can have a perfect square wave. Again, you are adding a counter. It's not the output of 555. You are adding a counter, but at least you can get oscillation at the output of the counter. And those oscillations can have multiple time period, but all the oscillations will have perfect square waveform with different time periods. The output of 555 is not going to be a perfect square wave. It's going to be a rectangular wave with high time to be larger than the low time. That is, duty cycle will be more than 50%. All right, example 7.3, we have a 555 timer. This is your RA, 1 kilo ohm, RB, 3 kilo ohm, capacitor 0.02 microfarad. Determine the high state time interval, low state time interval, time period, frequency, and the duty cycle. So just again plugging in the equation. High state time is 0.693 RA plus RB times C, 55.4 microsecond. Low state 0.693 RB times C, 41.58 microsecond. Time period is going to be the combination of both, addition of both, 97.02 microsecond. Frequency is one of the it's the reciprocal of the time period, 10.31 kilohertz, and duty cycle is simply high time over the time period, which is 57.14%. It will always be higher than 50%, of course, because high time will always be larger than the low time. A 555 stable multi-vibrator is providing the clock frequency to be to a 4-bit binary counter, as shown in figure 7.2. This. The frequency of the least significant bit of the counter is 16 kilohertz. Determine the value of RA and RB if the duty cycle of the timer's output is 70% and C is 10 nanofarad. So least significant bit is TA. So the frequency of the least significant bit FA is 16 kilohertz. And we have to find the value of RA, RB if the duty cycle is 70%. So duty cycle is 70% or 0.7. And capacitor is 10 nanofarad. Okay, so FA is 16 kilohertz means the time period will be 1 over 16K. And what will be 1 over 16K? Look at that. (6.25) what? Exponent -5. So 62.5 micro. 62.5 micro, right? Okay, so 62.5 microsecond. All right, so this is the time period of QA is 62.5 microsecond. Now observe that the output of 555 timer, the time period is half of that because time period is increasing. So this is the output of 555 timer, T out. This is 2T out. This is 4T out. This is 8T out, and this is 16T out. So the this is 62.5 microsecond. That means the output of 555 timer will be half of that. This implies the output time period of 555 timer will be half of TA, which will be 31.25 microsecond, right? 31.25. So this is the time period. Duty cycle is given 70%. Duty cycle is TH over the time period of 555 time. So TH will be equal to duty cycle times T555 timer. Duty cycle is 0.7 and time period of 555 timer is 31.25 microsecond. Calculate that. Yes. Say it again. They have what? Schmidt trigger. They have flip-flops inside. Counters have flip-flop inside. Yeah, they have 4 flip-flops basically. Do what? I'm sorry. Yeah, remember flip-flop is, they are stable in both states. So when the clock is going to activate them, they're going to go in one state. And then when the clock is going to activate them again, they're going to go in the other state. So that's what. Schmidt trigger is a comparator. But flip-flop, basically, they are oscillators. But both states are stable. They're just going to oscillate based upon when you are sending the clock signal. When you send the clock signal at the rising edge of the clock or the negative edge of the clock, whichever, at that edge, the flip-flop output is going to go high. And when then the edge comes again for the clock, the output is going to change again. So it's going to stay in one state as long as the next edge at the clock does not arrive. Right? So they are oscillators. Flip-flops are oscillators, basically. Yeah. They are stable oscillators. As we discussed, there are 3. There is a stable, they are monostable, and there is astable. So they are stable oscillators, flip-flop. All right, what is that? 0.7 times 31.25 micro. 21.875 microsecond. Okay, so this is the high time. So we know that TH is 0.693 RA plus RB times C, which is equal to 21.875 microsecond. And capacitor value is given as 10 nanofarad. So RA plus RB will be what? Calculate that. 21.875 micro divided by 0.693 times C. Yes. How much? What is that? 2.18 kilo ohm. Okay. All right. So that is, let's say, our equation number 1. Now, the other equation is gonna, one of the values is gonna come from the load time. Also, the load time is 0.693 or let me see, what is that? RB times C. And how much is the load time? Since we know the total time, 31.25 microsecond, and high time is 70%, so load time is going to be 30% of 21.85 microsecond. From that, we can find RB 0.693, TL over 0.693. So TL is going to be 30% of the time period, which is 31.25 micro divided by divided by 0.693 times. Calculate that RB. And once you have RB, then you can go to equation number 1 and calculate RA. Yes. Yes. 13. So 1.37 kilo ohm. So RB is 1.37 kilo ohm. RA will be 2.18 minus 1.37 kilo ohm. Yes. What is that? 800 ohm something? 810 ohm. RA will be 810. RB, you guys told me 1.37 kilo ohm, right? What did you get? 3.15 kilo ohm. Anyone? 3.15 kilo ohm. You got 3.15. Okay, so maybe the 2.1 is incorrect value. $3.15 kilo ohm. And is RB the same? Huh? Is RB 1.37 or what? 1.35? 1.35 kilo ohm is RB, which will give RA to be what, 2 point something? 1.8? 1.8. Okay. All right. So the important thing when you're solving this, of course, equations are pretty standard and they're given to you equations because again, I'm not asking you to do the derivation for those equations. The important thing is if you go to the circuit, then you have to identify what frequency is given to you. Like if the frequency of most significant bit is given to you, if FC or TC is given to you and TB, and then you have to relate that back to T naught basically. For example, if this time period or frequency is given to you, then you're gonna go back 16 T naught is this, 8 T naught is this, 4 T naught, and then T naught. So basically whatever is given, you're gonna divide that by 16 to get the time period. If this is given, let's say, 2 millisecond or whatever, then 2 millisecond divided by 16 is going to be the output T naught. And once you have this time period, then you can use those equations, 0.693 RA plus RB times C and 0.693 RB times C. So that's where I have seen some struggle in the past, that if like this problem is solved for the least significant bit for the 7493, but in exam, let's say I give most significant, and then a student kind of struggle how to relate that with the output. So just make sure to remember that time period is increasing as you go from least significant to most significant. Frequency is decreasing. So if the frequency is given to you, you have the highest frequency here, and then it will keep on decreasing. But when the frequency keeps on decreasing, that means the time period will keep on increasing. So just keep that in mind for 7493 as in which direction you have time period increasing or decreasing. Time period increases as you go from least significant to most significant, and frequency decreases as you go from least significant to most significant. So that's just one thing that, again, when people make mistakes, students make mistakes, so just keep that in mind when you're solving a circuit like that. And I believe this is the last example of this chapter.